Good afternoon. We are team number 140054 from St. Joseph's College, and we studied the geometric construction of triangles and also the algebraic interpretation of constructibility. The motivation for our project came mainly from the fact that we often came into problems of the nature given three pieces of information about triangle. It might be the side, the angles, the angle bisectors, medians or altitudes. Then we have to construct a triangle using Euclidean tools. Now, we're interested by this kind of question, and therefore we would like to find under what conditions exactly can this triangle be constructed, and under what conditions it cannot be. First, I would like to define Euclidean construction and a constructible number using coordinate geometry. On a Cartesian plane, if two points, 00 and 10 are given, then the following operations are called parts of Euclidean construction. First would be passing a straight line through two known points, called the straight edge operation. Second of which would be passing a circle through one point and using another point as the center, called the compasses operation. The third would be simply finding the intersections between circles and lines, so as to add new points to the known points. Now, if after a finite permutation of such operations, we can find a line, for example, the red line there, which has a length that is equal to the absolute value of a certain real number a, then this number a is called a constructible number. Then I would like to also define notations we use for the sides, which are capitals ABC, and the angles are small abc, well, reverse of what usually it is. And for angle bisectors, medians, and altitudes, we name them after the side they fall on, and then we use the prefix I for angle bisectors, M for medians, and H for altitudes. And we use this bracket to mean given conditions, three conditions, x, y, z, construct a triangle. For example, in case 1, we wrote this to mean given the three sides of the triangle, construct a triangle, which is the simplest case, of course. Also, I must define what an inconstructible case is. In our study, we define it as there being existing at least one combination of values for the conditions, the three conditions, such that a quantity essential to the construction is not a constructible number. Otherwise, it is called a constructible case. Now, let us first look at case 32, which is given one angle, a height, and a median on pages 45 to 47 of our study. This one, we use a conventional geometric construction method because it's quite simple. We use a little bit of algebra in the interpretation. We first have to construct a triangle that is similar to the desired triangle, and then we scale it up so that it becomes the desired size. Our line of thought was like this. Let's say this is the triangle we need, PQR, with median PM equal to MA, and height not shown here. Let's say its circumcircle is C1, its circumcenter is O. And let's say the midpoint of minor RQR is T. Join MT and mark an arbitrary point T prime on MT. Then we can mark also P prime, Q prime, and R prime on MP, MQ, and MR respectively, such that MP prime to MP is equal to MQ prime over MQ equals MR prime over MR equals MT prime over MT. We can show by considering similar triangles that, like PQRT, P prime, Q prime, T, R prime, and T prime are cyclic. So if we can construct T prime, P, and R prime, then we can use the ratio MP prime to MP to construct the other 2 points. So here's the construction. First, we construct a right-angled triangle, MHP, with MH equals MA and HP equals HA. And then we draw a line perpendicular to MH through M, call it L1, and construct T prime an arbitrary point on L1, and then extend MH past H to Q prime, such that angle MT prime Q prime is 90 degrees minus half A. And then I'll extend also MH past M to R prime, such that the angles MT prime R prime and MT prime Q prime are equal. Then I'll construct the circle of a triangle Q prime R prime T prime, which we call it C. And the intersection of C and PM, we call it P prime. Then we also construct a line through PL, which is parallel to P prime Q prime, and extend HQ prime to Q, such that Q lies on L. After that, we also extend MR prime to the other side to R, so that MQ and MR are the same. Then MQR is the triangle we need. A second case I will look at is fifth video, in which 3 altitudes of the triangles are given on pages 74 to 77. This case is more interesting because we have to use a little bit more algebra in the interpretation part. We have to first investigate the relations between the given lengths and the desired lengths. But after that, we can simply draw the triangle using purely geometric means, so that makes the case more beautiful. Here was a line of thought. For any triangle with sides A, B, C, and the corresponding heights as shown, altitudes as shown, the ratio of the 3 sides is equal to the ratio of the 3 reciprocals of the 3 corresponding altitudes. This can be easily proven by considering the area of the triangle. Now, so if you use the 3 altitudes to construct another triangle and mark the new altitudes, HA prime, HB prime, HC prime, then it's not difficult to see that the 3 new altitudes will also be proportional to the previous reciprocals. So if we use the new altitudes again to draw another triangle, we'll find this new triangle is actually similar to the first one we started with, because 3 sides are proportional. So in the first case, in which there exist 2 altitudes would add up to more than a third, then we can construct such a triangle PQR such that PQ is HA, QR is HB, and PR is HC, because it doesn't violate the triangle inequality rule. Then we construct the 3 corresponding altitudes, which are RS equals HA prime, PT equals HB prime, and QR equals HC prime. And then we move the 3 altitudes out to form another triangle, XYZ, with XY HA prime, HB prime, HC prime. And remember, this triangle is similar to the one we need. So we copy the angle X in rectangle triangle DEF so that D is equal to X, and such that EF is equal to HA. And we extend DE to G such that G is at a perpendicular distance of HC from DF. Then DFG is the triangle that we need. But unfortunately, it may happen that no 2 altitudes add up to more than a third one. In this case, the triangle with HA, HB, HC as the sides cannot be constructed. In this case, we have to construct a right angle triangle XYZ such that XY is HA, YZ is HC, and construct a point V on YZ such that VY is HB. We construct W on XY such that WV is parallel to XZ. Then after this construction, you can see that WY is equal to HA times HB over HC. Remember that. Now we construct another triangle, DE with DEF, with DE equals HA, EF equals HB, and DF is equal to WY that we just constructed. This can be constructed, must be constructible. It is shown in our study. We then construct a line that is parallel to DF and at a perpendicular distance of HC from it. And we extend DE all the way to L and mark the intersection point as M. And we extend DF to N such that MN is parallel to EF. And voila, DMN is the required triangle. Now, for most of the other cases, they are not quite so beautiful. They require much more algebraic interpretation. For such cases, for a few cases, we had to use coordinate geometry, which was the most powerful tool. But then for most cases, we had to set like a billion variables, but not quite so much equations. So the problem is we are left with so many variables and so few equations, we can't even solve them. So we're taking this step. We substitute all but one variable with arbitrary, yet suitable constructible numbers, such that the remaining variable may be expressed in the form of a polynomial. So our target becomes this. We have to determine how a polynomial with non-constructible roots can determine whether it's non-constructible roots, such that it can be a constructible case. We'll talk about case 13, which is given 2 sides and one of the angle bisectors on 21 to 22. Let's say this is the required triangle with PQ equals A, PR equals B, and the angle bisector marked out in blue. Let's say the angle bisector is X, and half of the angle is theta. Consider the case when we substitute A equals 2, B equals 1, and X equals 1. Then we also let Y equals cosine theta. Then we arrive at this equation. Then we have to use the 2 to the power rule, which means if a number alpha is constructible, then the degree of its minimal polynomial must be of the form 2 to the power n for some natural number n, where minimal polynomial of alpha is the monic polynomial of at least degree among all polynomials with rational coefficients we have alpha as a root. Evidently, 3 is not a power of 2, so y is not constructible, and theta is also inconstructible. Formal definition, we label this case as inconstructible. That's the end. Thank you.